what we can do is add error bars. So on the bottom right, there's error bar calculations. And what we can tell it to do is use a certain column for its error bars. And the error bars we already created, or we already entered, is the column under systematic uncertainty. Okay, so that column, and they're going to be very small. In fact, I might have to change my circles to, instead of medium, I might have to make them small for you to actually see them. Okay, you should see, it should look like a TIE fighter if you guys are Star Wars nerds. Okay, you should see little bars now around your circles. Let me show you how I did that again, okay, right from scratch. I right-clicked anywhere on the graph, column options, and I went to launch height, or the x-axis, which is launch height. I found in the pop-up window, I clicked error bar calculations and told it to use the column systematic uncertainty. Okay, so it's using those as the error bars. And we're going to repeat the process for the y-axis. But instead of systematic uncertainty, we're going to use the random uncertainty values. So column options, range, error bar calculations, tell it to use the column random uncertainty. These ones should be bigger. Okay, I'm going to come around and help you guys out. I'm going to pause the recording. Okay, class, I'm ready to keep going. Quiet down again, please. Shh. Quiet. Alright, we are going to fit two curves through this data. One of them is going to be an automatic fit based on your actual experimental data, and one of them is going to be manual calculation based on what the theoretical function should be. So let's do the automatic one first. Okay, now, what we're going to do is, in the top, you're going to click on Analyze. And this is the reason that we copied all this data into Logger Pro, is because Logger Pro is fantastic at doing nonlinear analysis. So instead of a linear fit, we know that it's not a linear fit based on our theoretical calculations, it's a curve fit. And I don't think it actually has it in its... No, it doesn't. We're actually going to have to create our own theoretical function here. So, under curve fit, we want to define our own function. And we're going to call it square root. Okay, it's a user-defined function. Logger Pro recognizes that if you use capital letters, those are variables that you can change. And the lowercase x is the x-axis. So it's just like typing in an equation. So the function that we're going to try and fit through it is a times the square root, which is sqrt. So a times sqrt of x. And again, we're just mimicking the function y equals k root x. Okay, that's the function that we're trying to mimic. And what the computer is going to do, what the program is going to do, is work out what's the best value for a that we can fit through your data points. Okay, so a times the square root of x, and if we click OK, try fit, there you go. If you click try fit at the bottom, it should automatically generate an a value. 0.8261 was the a value that mine generated. Yours will be different. So again, we created our own function, a times the square root of x, and then by leaving this fit type to automatic, it's telling the computer, okay, try your best to fit that curve through our data. And it looks like it's actually not too shabby. What's that? All right. Let's hop back into Excel for a second. Actually, no, I'm gonna... Okay, so once you have that calculated, once you have that theoretical coefficient calculated, we're gonna create another curve, superimposing it on the first one, so you can actually see visually what the difference is between your experimental curve and your theoretical curve. And it looks like it ends up being a pretty neat looking graph. So again, I'm going to do analyze. I'm going to create another curve fit. This time, instead of automatic at the top, we're going to switch it over to manual. Okay, this time instead of automatic, we're going to switch it over to manual. And you type in your theoretical, gentlemen, you type in your theoretical A value. For the group that I was copying their data from, it's 1.105. That actually wasn't too bad. It was pretty close. Yeah. Could have been worse, absolutely. The vertical height from the entrance of the tube to the exit of the tube. Okay, vertical height. Vertical height from the entrance of the tube to the exit of the tube. Yeah. All right, I want us to come around and see what your graphs look like. So, in order to calculate the percent error, it doesn't matter. You can do it on separately, but I'm just going to show you in Excel. So just hop back into Excel, and we can do theoretical coefficient. And we can do experimental coefficient. And we can do percent error. So the theoretical coefficient was the manual fit one that you entered, which is A equals, for me, 1.105. The experimental coefficient is the one that the computer tried to fit through your data, and it's 0.8261 for me. Okay, and the percent error calculation, you've been doing this since grade 9. So equals the absolute value, okay, we don't want plus or minus, of, and I'm opening up two brackets here, experimental minus theoretical divided by theoretical. Oh, and times 100.